Hi, my name is Ben Dribbis, Director of Artificial Intelligence at William Carey University, where I serve as Chair of the Math Department and also do research with the College of Osteopathic Medicine. And I'm really excited to share with you today some of my medical AI research involving women's health. This is part of an NIH-funded grant that I recently obtained through the Mississippi IDEA Network for Biomedical Research Excellence, or INBRE, and I want to thank INBRE and everyone else who's been helping me with this ongoing project. So the objective here is effective medical AI, enhanced by some novel AI methods that I recently patented. And there are three specific aims to the NIH grant overall, but today we're going to focus on just the first one, which is preterm labor prediction. Just a brief word on motivations. So the main motivation here is just the medical importance of this topic and the opportunities offered by AI to address it effectively. This is what you could call the AI rapid integration era in medicine, where great tools have been pioneered, but immense opportunities still remain. Now, I'm bringing some novel AI methods to the table, but these are specifically biologically inspired. They're not just borrowed from computer vision or natural language processing. And this is a highly application-focused project with AI architectures that are built from the ground up with the specific problems in view. So our focus today is preterm labor prediction. Now, this is a very common problem involving anywhere from 5 to 10% of labor events, depending on how you define the threshold for preterm, and has a very high cost, particularly human cost. Now, we're using a high-quality data set involving hundreds of thousands of pregnancies from the Consortium on Safe Labor, and our goal is to offer a clinical tool that will provide an updated risk profile every time a woman visits her doctor during pregnancy. We published a preliminary study pioneering these methods in the American Journal of Obstetrics and Gynecology in 2023, and our current study improves on these results and promises to shape these methods into an actual effective clinical tool. So I'll briefly review equipment and methods. We have good hardware available. We're taking advantage of all the standard methods like convolutional neural networks. That's one of the standard architectures shown here, along with all the standard software like TensorFlow and PyTorch. But we also have the novel methods and we have novel software to implement them. Now, my novel neural networks that I just patented are called Sparse Local Highly Connected Artificial Neural Networks, or SLC networks. And they're biologically inspired by phenomena in genetics and immunology called linkage disequilibrium. And that's why I'm showing the DNA strand here. But it would kind of distract from our focus to explain all these details now. So I'll just say that qualitatively, these networks work by effectively assembling local features in data like convolutional neural networks do, but then also simultaneously rapidly assembling non-local features without using costly dense layers, and they're highly efficient. These networks work by using a hybrid fractal structure like you see in the image here, and this provides a huge advantage in network connectivity over standard architectures. And this allows for very rapid feature assembly for the composite features that you often encounter in biology. For instance, you don't typically see a single eye, you'll see a pair of eyes. And my patent explains the details of all this if you're interested. Now let's go into depth on the preterm labor prediction problem based on this novel AI tool. So we're developing an individualized, non-invasive, cost-effective clinical tool that's significantly more accurate than standard statistical methods. So for comparison, here are some existing accuracy results and methods from the literature. We see 65.1% accuracy using long short-term memory, 70% using gradient boosted trees, 70.9% using logistic regression, 72.7% using AdaBoost, 75% using gradient boosted trees again, 79.2% using transformers, 82.2% using long short-term memory together with the attention mechanism. Of course, the attention mechanism is what characterizes transformers as well. And then 82.7% using recurrent neural network ensembles. Now, these last three methods here are considered to be computationally costly, heavy architectures, and our methods are much more lightweight and efficient than these. So let's discuss these methods in detail. So we're using ensembles of highly efficient SLC networks. These are the new ones that I just patented. An ensemble means a family of networks that each give a virtual expert opinion, and then these opinions are combined to give an overall prediction. Our approach is going to be broken into a statistical study, a demo study, and a comparison study. And the ultimate goal, remember, is to deploy a clinical tool that outputs a constantly updating risk profile. So for this purpose, the statistical study will quantify the accuracy of this tool, the demo study will show how it works practically, and the comparison study will compare it to other methods. And I will carefully explain how we chose variables for this model, how we pre-process the variables, and then I'll separately talk about the statistical study design, the demo study design, and the comparison study design. So let's discuss how neural network ensembles work. So each member of an ensemble is an artificial neural network, and this consists of an input layer where data is fed in, several deep layers where data is processed, and then an output layer that makes a prediction. So in our case, each network can give either a positive result or a negative result, and then the ensemble result depends on whether positive or negative results predominated. Now here's an actual SLC network, one of the new ones used in this model. And you can see it's more complicated than the schematic pictures that I showed up here, but it still is very lightweight and efficient compared to most other models. Okay, let's discuss variable selection for our model. We used a Bayesian approach, and this means that the model constantly updates the risk profile as additional information is provided. And we were very, very conservative about our accuracy claims. We actually set aside some variables that could improve our top line number to avoid possible confounding effects. And our model is flexible enough to accommodate any individual patient. We're able to adjust variable selections for each patient depending on what is actually known at any given point during the pregnancy. And we're able to update the model every time new variables come into the picture, and we adjust the neural networks accordingly. Now let's outline the categories of variables that we use. So these include race of the mother, 4 variables, marital status, 2 more, education level, 2 more, insurance type, 3 more, medical history, 23 variables, lifestyle choices during pregnancy, 3 variables, and then indicators during pregnancy. This is 40 variables, and it's a total of 77 variables. Now here's an exhaustive list of all the variables that we used. And the yellow highlighting over here shows how the list of variables were updated in the demo study, going from pre-pregnancy to first trimester, second trimester, and so on. We'll go back to this later. So pre-processing the data involves some details that I should briefly mention. First of all, real data sets, any real data set you find will have missing values, and these have to be inferred or estimated effectively. Second, variables that belong to discrete categories like race must be preprocessed differently than integer or real valued variables like number of previous pregnancies or BMI. And I'm not going to discuss the details of standard methods that deal with categorical variables or integer or real valued variables, but these do play a role. So an important factor in this study is class imbalance. And what this refers to is that normal term labor events greatly outnumber preterm events. Now, we chose a threshold of 34 weeks gestational age for preterm labor because this is where serious complications become common. We want to know before 34 weeks, after 34 weeks. This is about a month early. And this translates to about 5% of pregnancies. Now, this graph shows the actual distribution in the CSL data set of per week, labor events per week. So for effective model building, it's necessary to overemphasize the effect of the preterm events, and we'll revisit this below. Now let's discuss the details of the statistical study. And remember, the purpose of this is to precisely quantify the accuracy of the model. So we split the data set into a training set and a testing set. The training set is used to train the neural network, while the testing set is used to evaluate the accuracy of the resulting models. And the 50-to-1 split here is statistically justified. Ask me about it if you have questions. I already mentioned the class imbalance in the data set, and we oversampled the class of actual preterm events to counterbalance this. Again, I'd be happy to answer questions about it. And I showed this before. This is one of the novel neural network models we use that gives good accuracy with great efficiency. We used ensembles of size 99 in the statistical study. And here are accuracy results for the statistical study. So the ensemble accuracies were 80.5% plus or minus 0.3% for the positive testing data, 85.9% plus or minus 0.1% for the negative testing data, and this gives a balanced accuracy of 83.2% plus or minus 0.2%. We use balanced accuracy here because the positive and negative classes are roughly of equal importance. And that's because even though the negative set's much larger, each preterm event carries significant risk. So we kind of we add weight to the importance of that class. So the average individual network accuracies were 79.9% plus or minus 0.3% for the positive testing data, 84.8% plus or minus 0.2% for the negative testing data, and this gives a balanced accuracy of 82.3% plus or minus 0.2%. So we see that working with ensembles gives several advantages. It gives a risk index or profile instead of just a yes/no answer. It gives better stability, and it also gives better accuracy. So now we turn to the demo study design. And remember, our goal is to simulate how this tool would actually be used during pregnancy. So the patient's individualized model is going to be updated at each doctor's visit to provide a running risk profile. We used a hypothetical 4 visits for simplicity, and this is pre-pregnancy, first trimester, second trimester, and then early third trimester. And this shows how the variables are updated for each of those visits. Now, in practice, more visits would be included. You could go to the doctor, a dozen times or something, and the tool would be updated each time. So this graphic shows how the risk indices change for the pregnancies that ultimately did end in preterm labor. So each thick transparent line represents a pregnancy, and the darkness of the color shows how many accumulated at each risk level at each time. The -1 here corresponds to the baseline risk of about 5% before you know anything about the patient. And then 0 is pre-pregnancy, including data up to and including medical history. 1 stands for first trimester, 2 for second trimester, 3 for third trimester, early third trimester. And you see the model picks up a large percentage of the upcoming preterm events early in pregnancy and then adds progressively more with each individual visit. Now this graphic shows the same thing for the pregnancies that did not end in preterm labor. And again, you see the model gives the correct answer for most of these pregnancies relatively early. Here are the numerical results for the demo study. The pre-pregnancy accuracy was 58.5% for the positive data, 68.6% for the negative data, and 63.6% for the balanced accuracy. For first trimester, we saw significant improvement up to about 73.6% for balanced accuracy. And then second trimester up to 76.4%. And early third trimester, we hit 83.1%, which matches the expectation from the statistical study. So here's another interesting way to view the results from the demo study. This graphic shows the final values of the risk index for the pregnancies that did end in preterm labor. And you see most of these had a very high risk index. And then this graphic shows the same thing for the pregnancies that did not end in preterm labor. Most of the risk indices are very low. So finally, we discussed the comparison study. And remember, the purpose of this study was to test our model against other common machine learning and statistical methods using the same data set and the same preprocessing. So it's a little different than the literature study because that mostly used different data sets or different preprocessing. So this graphic shows results for a spectrum of different models. And these include statistical models like linear regression and machine learning models like neural networks. And not all the models we tested are in this graphic here. So we also tested a spectrum of different choices of oversampling to deal with the class imbalance problem. We recorded results for positive, negative, and balanced accuracies, and the figure shows balanced accuracies with error bars. So here are the numerical results for 7 different models. In the comparison study. Poisson regression gave 80.0% balanced accuracy, linear regression 80.5%, logistic regression 81.5%, dense neural networks 80.7%, convolutional neural networks 81.5%, and then individual SLC networks, these are the new ones, gave 82.3% accuracy. And then for the model we used, which was ensembles of these new networks, 83.2% accuracy. And you can see the error bars in these results are small enough to demonstrate clear superiority of our model over the others. And while the differences might not seem to be very large in terms of absolute percentages, this does translate to providing correct answers for thousands more preterm events and tens of thousands more non-preterm events per year, which can give a significant clinical impact just because of the number of pregnancies involved. So there remain some important tasks to be finished for this project. First, we need to refine and expand the literature study. And then there are some additional metrics we can add that can shed additional light on these models. Third, we've mostly finished the manuscript for this, but it needs to be finished and submitted. And then fourth, we've identified some clinical opportunities to begin to apply these methods in practice, and that's exciting. And then finally, there's some technical tasks like writing data entry apps. All right, so that's all for today. I would be thrilled to answer any questions you might have or any suggestions or any other feedback. Thank you so much.